predicting the qualitative acid-base properties of salts. Now, you do not really need to perform any calculations to do these kind of problems. The most important thing is to look at each of these solutions and break them apart into their cation and anion components, and then decide if the cation is neutral or acidic. Those are your only two options, neutral or acidic. A cation is neutral if it is the countercation of a strong base. For instance, sodium hydroxide, okay? Hydroxide is a strong base, sodium ion is pH neutral. Or a cation can be acidic. 2 times a cation can be acidic is if it is a small, highly charged metal, like a transition metal, like, I don't know, cobalt 3 plus, because that will attract water molecules to an aqueous solution to form a hydrated complex, which can then donate protons and act as an acid, Lewis acid. Or more commonly, that cation is the conjugate acid of a weak base. Okay, so let's have a look at this species. So if I was to break this apart, I'd break it up into a cation C2H5NH3 plus, and then the anion component is Cl minus. So to be successful at this problem, you really have to be practiced in looking at compounds and like imagining it's an ionic compound and breaking it up into a cation component and an anion component. Okay, if we go ahead and do this for each of our species, and then we're going to look at whether they are acidic, basic, or neutral. So talking about the anions, anions can only be neutral or basic. An anion is neutral if it is the conjugate base of a strong acid. So you know, like 7 strong acids, right? Hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid, chloric acid. If it's one of those 7, then the conjugate base, the anion component of that acid, has got 0 tendency to undergo hydrolysis, which is reaction with water, okay? Because that acid will 100% dissociate, that equilibrium lies 100% to the right. So basically the anion is going to be inactive. Okay, so if I take potassium iodide, that is going to break apart into the potassium cation and the iodine iodide anion. Let's see, what else have we got here? C5H5NH plus will be my cation, and Br minus, the bromide ion, will be my anion. And then I have sodium nitrite. So sodium will be Na plus and nitrite will be NO2 minus. So let's look at each of these ions in turn. So like I say, the cations, your choice is that they are either going to be neutral or acidic, and anions can either be neutral or basic. So if we look at this first cation here, C2H5NH3 plus, oh, I don't recognize it. However, I've been given some information in the question. Ethylamine, C2H5NH2, has got a Kb, base protonation constant. If I add an H plus to that, I get this C2H5NH3 plus fragment. So this must be the conjugate acid of a weak base. So this is going to be acidic, and the reason for that is it's the conjugate base of ethylamine, of a weak base. Sorry, conjugate acid of a weak base. There you go, trying to make it fit. So it's acidic because it's the conjugate acid of a weak base. Okay, what about the chloride? Well, HCl is a strong acid, right? So the chloride anion is going to be neutral, okay? It's the conjugate base of HCl, which is strong. So let's put a strong acid. Okay. So let's look at our next combination. Potassium would be neutral because that is the countercation of a strong base, which would be KOH. So that's a strong base. What about the iodide? Okay, iodide ion should also be neutral because that is the conjugate base of a strong acid. That would be hydroiodic acid. Okay, so what have we got next? C5N5H5NH plus. So let's take a little bit of a look at this one then. Well, is cation. If I look at the information I've got pyridine is a base, so we've got a Kb, base protonation constant for that. So that must be a weak base. So C5H5NH plus is the conjugate acid of a weak base. So that itself must be acidic. And the bromide, again, that is the conjugate base of a strong acid. That would be hydrobromic acid. So we can just go ahead and say that is neutral. Okay, so lastly, sodium. Obviously, it must be neutral because that is the counter cation of our favorite strong base, sodium hydroxide. So that is going to be neutral. And then the nitrite anion, and if you're not sure, just add a proton to it, you get HNO2. That's nitrous acid. That's a weak acid. In fact, it's one of the ones written up here. Nitrous acid is a weak acid. So we know that that is going to be its conjugate base, right? It is the conjugate base of a weak acid. So it itself will be a weak base. Okay, so now we have to rank them in order of increasing pH. So obviously the lowest pH is going to be the most acidic and the highest pH is going to be the most basic. So we've got one salt that is acidic here and another salt that is acidic here. So we're going to have to decide which one is the most acidic. So right now, we can definitely say that the highest pH is going to be this NaNO2, right? So low pH is obviously going to be most acidic. And then the high pH is going to be the most basic, and we're going to have something neutral in the middle. So we can kind of organize what we've got to some extent. So we know the highest pH, the most basic, is the only one that is a basic salt, and that is the sodium nitrite. That's going to be up here with the highest pH. And then below that, with a lower pH, will be our neutral salt, which is the potassium iodide. And so we have to decide out of our C2H5NH3Cl and our C5H5NHBr, which one is most acidic. So the way you can do that is look at the values of Kb, and we can do this very qualitatively, okay? Because Kw, the ionic product for water, is found by multiplying Ki times Kb, okay? So the bigger the value of Kb, the smaller the value of Ka, okay? So like larger Ka is going to be more acidic, lower pH. And on the flip side of that, smaller Ka is going to be less acidic because we've got less ionization, less acidic, and it's going to be at a higher pH. That's all we need to know. So out of these two, the Kb value is bigger for the ethylamine, right? 10 to the minus 4. So this one, Ka is going to be smaller. Okay, so this one is going to be less acidic. And that is going to be the higher pH. Okay, and then the Ka value for the C5H5 NH plus is going to be bigger because the Kb value for pyridine is smaller. So that's going to have a higher Ka. More acidic, lower pH. So if you absolutely have to see the numbers on this, you can, okay? So let me fill these in terms of order. So my lowest pH is going to be the C5H5NHBr, okay, because of pyridine being a weaker base, therefore the cation, the conjugate acid, is going to be more acidic. And then C2H5 NH3. These are so similar formulas will be in there somewhere. Okay, so that would be the ordering that I'd put them in. If you have to do the numbers, well, the value of Kw is 1 times 10 to the minus 14. That is a fact. So what you can actually do, if you have to, is go ahead and solve for what Kb sorry, Ka actually is, so you can look at the absolute numbers, okay? So if you want to, you could go ahead and do that just to be sure, Okay, so if we take the C2H5NH3, Ka is going to be Kw divided by whatever Kb was for my ethylamine, so that's going to be 1 times 10 to the power of minus 14 divided by, let's see, Kb for the ethylamine was 6.4 times 10 to the power of minus 4. So what is that going to shake out to be? I don't know. That's going to be about 1.6 times 10 to the power of minus 11. Excuse me if I made an error on that. I did it in my head. So that'd be my value for Ka for that one. So let's rinse and repeat that for, yep, that's gone weird. Whatever. For this guy right here. Stop it. Right, give me a text box. That went wrong. So if I take my Kw, oh no, I lost everything. Oh, can I do it? Can I do it? This is the trouble with using my shortcuts. Oh, okay, there it is. It's back again. Hooray! Okay, so let's do the same to calculate Ka here for my C5H5NH plus the conjugate acid of my pyridine. So that'll be Kw over Kb for my pyridine. So that'll be 1 times 10 to the power of minus 14 divided by pyridine was 1.7 times 10 to the power of minus 9, and that will shake out to be 5.9 times 10 to the power of minus 6. So we can see the magnitude of Ka is much bigger, 10 to the power of minus 6 versus 10 to the power of minus 11. So this C5H5NH plus is a stronger acid than C2H5NH3 plus. So again, that matches with what the order we put here. So I guess, hang on, the one with the solution that had the lowest pH, well, that is this guy. And then 2. So those were the main two that was like a little bit more tricky to sort out. Like I say, you don't have to do the math. It does say predicting the qualitative acid base properties. So you can just use the fact if Ka goes up, Kb goes down, and vice versa. The bigger the Ka value, the more acidic, because more hydronium is being released, therefore the lower the pH. But you know, and of course our highest pH is going to be that basic salt, that sodium nitrite. So hopefully that helps.